Let's go ahead and get started. Where we left off on Wednesday, I think we basically covered the main functions for doing file I/O, but then there's really a separate programming task that's kind of on top of that low-level functionality that's using fprintf, fscanf, fread, fwrite type functions, which is applying some sort of format to a file, or conversely, parsing a file that is adhering to some type of format. And we need to have these formats, and this is how we can exchange files, and people can write a file on one computer and open and parse and read that file on another computer. We've already used to some small extent the CSV file format this semester. That's probably the simplest possible format really to just lay out some hybrid type of data in a file. As the name suggests, it is values that are separated by commas. Now, even having said that, CSV is one of those sort of quasi-standard, and you can have CSV files that are separated by spaces or by semicolons or by any kind of custom character in between them. But conceptually, for a table on the right, they tend to look something like this, where there may be some sort of header information here separated by commas, and then each line in the file is going to correspond to the corresponding entries in that table, separated by some delimiter, separated by some comma. And so the design exercise we'll go through relatively quickly today is to parse a CSV file. Mentioning first that to parse a truly arbitrary CSV file, if I said, write a program that could read and print out any CSV file I can generate, that's actually a fairly challenging programming task. And that's just for CSV files. When we start to talk about some of these other data storage formats, these other file formats, this is some of the hardest programming tasks really available. Some of these terms you may have heard of, but if not, you will eventually hear more about things like JSON file format, JavaScript object notation. It's a very popular data interchange format for web applications. When you are surfing the web, you are actually passing back and forth these files pretty much continually. At first blush, they don't look that much different than CSV, and ultimately you have values and you have to have some way of categorizing and separating these values. So they're all going to look sort of similar at first blush in any case. And it's going to look a little bit closer to something like this, where you have named objects and you have then values associated with those named objects, these attribute value pairs that you have here. That's one other common, very commonly used data file format. In the more scientific computing field, you have things like YAML or XAML or markup language based, XML based data formats. It's very commonly used in Python. It also has some sort of compatibility with JSON in sort of a more theory than in practice kind of sense. But again, in some sense, there's nothing new there, which is to say you have some pairs of attributes and some values corresponding to attributes. That is the case for CSV, that's the case for JSON, that's the case for YAML. They're all going to be some sense of that. But to parse an arbitrary version of those files is in fact a very challenging programming task. And I wouldn't give that to you as a homework assignment in this class. Now, conversely, if you're on your next internship or your first internship and you're told, I need you to build a JSON parser in C, perhaps, for this application, from what you've learned in this course, what's the first thing you should do? You've been given the task. All right, I need to parse JSON files in this application. What should you do first? Quit. No, that's not the answer. It's a high-paying internship and you need the money. You're given a new task to do something that possibly has been done before, right? Look at what else. Look at what else is out there. Absolutely. Don't necessarily try to reinvent the wheel, right? We are in this classroom environment where if I tell you to implement something, it's because I want you to learn something along the way. Sometimes in your internships, there may be a little bit of a flavor of that as well, but in general, they care more about, let's get this piece of software working within the constraints that we have as a company for the timeline that you have. We could take a look at these. I haven't clicked on them today, so I won't click on them right now, but these libraries do exist. C isn't necessarily the most common programming language to parse those particular types of files. Because of the downsides of C, as we've already experienced this semester, they're not commonly used for parsers in general, but these libraries do exist out there, and probably they're going to do a better job of it than you were if you were to write such a thing from scratch. So that should be your first task, which is, okay, I have this new particular file format I have to handle, taking my word for it that it's not a trivial task. That would be more than your entire summer internship to build such a thing yourself. Let's learn how to use an existing library to be able to solve part of our problem. It's probably not solving the entirety of your problem. You are going to be parsing JSON files in order to do something with that data. So you're still needed, you're still programming, you're still a software developer, you're still writing code, but you're not really focusing on this task that's already solved, at least to some extent. You're using someone else's code. For CSV, for a particular CSV file though, the skills we've picked up this semester should be sufficient to allow us to play around with that. It's a more tractable kind of task. When we are going to parse a file, we really don't start with code to begin with. We start by inspecting the file, looking at what is actually in the file, and then start to understand from that what kind of data types potentially make sense when working with this file. So this is the CSV file that I downloaded of the 2016 Chicago Cubs starting lineup here. And some of this may be baseball specific, which isn't necessarily my point. But there's a header row here which gives some sort of name associated with each of the individual data fields that are following. And there's quite a few of them here, right? We can kind of, depending on how much we know about baseball, we can kind of look at this and kind of guess. Well, that first thing is an index of something, right? Second one, POS, that's position. We have we've named, so first name and last name. Age, games, that's probably games played, etc. Plate appearances, at-bats, runs, hits, blah, 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 blah. We can start to look at that, and there's a lot here, so we won't go item by item necessarily. And your first thought then should be, okay, I'm going to have to eventually write some fscanf style code here to scan that out with our commas in between things. But I think in order to write code that's not going to be completely untenable to maintain, you should really think next in terms of what data structure do I need. And here I mean in terms of like the struct, definition in C here. And depending on what the actual task is, here the task isn't all that clear. It's really parse this file. So if you get it stored as a variable and you can print it back out, you've succeeded in that sense. We could sort by batting average and do stuff like that if we wanted to, but I don't think we have to go through that final step here today. But that really should be your first task, which is understanding that you have this many data fields, and let's drag this over so we can actually see all of it. And can we now go through and design as part of our structure what each subcomponent of that structure would need to be in order to read entries corresponding to that. I've already done a little bit of that for you in this initial code that we have here. And it is meant intentionally to effectively be a one-to-one relationship between the entries in that file and then variable names in our C structure here. With a small kind of simplification that I didn't do it in the same order. I put all the ints first, and then there's a bunch of floats, and then there were some things left over. The tricky part when parsing even a CSV file is you kind of have to get it exactly right. If you are off by one data value you're trying to read in, your subsequent calls to try to read the rest of the line aren't actually going to work correctly, which is what makes this problem to solve in a more general sense quite a bit more difficult. If I had the same exact file, but Javi Baez's stolen bases was deleted for whatever reason, that task becomes quite a bit harder. Identifying that happened, kind of correcting for when that happened, maybe entering 0 in the case when that happened, that actually becomes a much harder programming task. I don't think it's something we couldn't handle given enough time, but even with a well-formatted, every entry is there in every location, this is not a trivial programming task. But that's what we had here. For these corresponding entries here, from rank to intentional base on balls to some just additional name and index, we then have a corresponding entry in our structure. So that's how we can get started. We also don't necessarily know when we're parsing a file. We talked about this a little bit on Wednesday. Well, how much data do I actually have? If I tell you you have 15 players, then when it comes time to actually allocate my baseball players, if I know it's exactly 15, I probably don't worry at all about dynamic memory allocation. I just call it a statically allocated array because I know I have exactly 15 and I don't have to worry as much about dynamic memory allocation. In this case, we don't necessarily know until we've read the entire file how many of these things do we have. And so you do then potentially also have to use dynamic memory allocation, where whether you allocate it one by one as you go, or you allocate a block and then only use some subset of that block, that's a design decision we can make. But we have to kind of keep track of how many players have I currently parsed, how big is my structure going to be corresponding to that player, and to kind of keep track of that data as I go. Okay, we have a file called chicubs2016.csv. Again, that extension is just for other utilities to be able to read it. It looks like Replit does take that extension into account, but it doesn't really seem to treat it like a CSV file in any meaningful sense. It just gives it a green little icon, which is not terribly helpful here. It does say comma separated values, well, because something's busted. But still, it at least recognizes that it's a .csv file. How do we get started? We got to parse this file. What do we do first? Cannot start yet. We cannot do a for or while loop yet. We will soon. We gotta crack open this file first. We gotta crack open this file, check that it actually works, right? So again, what we call that file, that's like a little handle to keep track of this particular file. fopen is the function we use for that, right? And it's easy to forget, but there's that second argument that I'm gonna open this in read mode. And the truth is, if you accidentally open it in write mode, you've blown away your file. So make a backup of that file, right? Or use the history feature to get it back if you need it. So put that R in there first. Only when you're sure you're editing and writing a file do you put the W in there. And sure. We looked at that briefly the other day, but I said it wasn't necessarily as commonly used. There's read extended, and supposedly that allows you to both do the fprintf and fscanf in the same file at the same point in time. That's less common. Very often we do a full read of the file, and then if we have to, we go back in and we update things in our file. That stands for read extended. So there's our CSV file. It is still good practice to check, hey, did we get a null pointer back out? If so, inverse of that will lead to a positive result, and we should provide some sort of error message. Cannot open the CSV file. And just get out of here. There's no recovering from that for this particular program here. Then we do want to have some sort of loop to read from this file. But first off, the data in that first line is actually not super relevant for us in terms of, we needed to have that there to even know what this data was all about. In terms of parsing that into our structure, we actually don't really need it, right? We do have to read it, we have to get past it, but we can kind of read it and forget it here. So what you could potentially do is, and maybe we can define this up here, we can have some sort of line buffer, and they're just typically called that, and we give it enough space so that we don't accidentally overwrite that buffer like someone's project code is currently doing. We set up a line buffer of a sufficiently large size, and we're just going to read that buffer. If we want to read the entire line, we don't want to use scanf, right? Or fscanf. Fscanf looks for very particular things, and you have to match those very particular things. We could probably build up an fscanf line that would read that entire line and store the results somewhere, but we really just want to read the first line, and that would be the comment here. Get the first line, and yeah, we can print it. We can print it. And that can be our first kind of milestone to say, okay, we've actually gotten our first line. That's that fgetS function. And I recall, and fortunately it's written here, the buffer is first, the number of bytes we are reading is second, and then the file pointer is third. I'm going to kind of put those in backwards. So CSV file is the last thing. The number of bytes, it's up to that many bytes, so you can put the entire buffer array in there, and then you provide the actual pointer to the buff that you are wanting to read from. So line buff, overwrite up to 1024 characters. It should be, yeah, go ahead.
Instead of putting 1024, putting the size of line buff. That way, if you change line buff, that will also change.
Yeah, and size of line buff, well, Let's test that. I always get this slightly wrong about whether size, well, string length won't work. Yep. Size of is a little tricky in terms of what it does and does not do. And it does print out 1024. So yeah, we could do size of line buff. If it's dynamically allocated, size of just returns the size of the pointer. And so as a general sense, that approach doesn't work, but we can do that. I like your good practice there. Because if you do change that later on, then your code's not correct. Or you do, max line size, 1024 or something like that. And then you change that and everything else works. I like it. Okay, and having now just printed it out, we did successfully print out that first line. So we kind of got the first line and then print it and then kind of get rid of it here. So the next step, now we have to have our loop where we are going to read from within our file, and there's a lot of different ways we can do this. We can certainly check why we have not actually gotten to the end of file. Keep going until we're at the end of the file. You could probably also do like a do while loop because the next line should be valid, otherwise there's no interesting data anyway, but for now that's fine. While we keep going here, we need to read in a new line, Read in a new line. That code could be exactly the same. And if we want to kind of test it real quickly, we can do that as well. Read in, print it out. Read in, print it out. That should basically give me just the entire file. And it does, looks good. One thing I added to kind of simplify the task, if you didn't want to use end of file, I added a fake data entry. And if you knew that in your file, good old final player Fakington, you could check for that, and then that's how you know you're at the end of the file once you've reached this kind of fake data entry that was added at the end. I'm a big fan of Fakington, but his career never really took off. Okay, so we read each individual line, and now we need to allocate space for a new baseball player. And this is the part, based on the code I have been seeing in the last few weeks of the semester, we still need to get good at, but I did say that when we introduced this topic of dynamic memory allocation, this is kind of a multi-month, even year journey that you're on in terms of getting better at it. But for now, we add the comment, allocate a new baseball player. We have kind of an empty pointer or a null pointer to what could be an array of baseball players. I also created a local one here, which we may or may not use. I just had it as a setup. We also have a variable that hopefully keeps track of the number of baseball players we've currently read. We could start by, let's increment that value. We have one baseball player. We now need to allocate, given what we previously have allocated, because this is going to be in a while loop, one more baseball player. And so if I wanted to do that better, I would probably say, not a new, allocate one more baseball player. If we already have an object and we want to change the size of that object, what function do we use? There you go, reallocate. We could use malloc and kind of play around with pointers here. Realloc is the correct function for that. Take an existing object, and even if it's null, it'll still work for us, and allocate a new amount of things for that. The syntax for that looks a lot like malloc, but not exactly. We're going to overwrite that pointer. It likes to have a nice cast for that pointer. Then the function is called realloc, which is where we're starting with. We want to reallocate this one. And then we tell it how many bytes we want to allocate. We know how many players we want to allocate. In this case, it was 0, now it's 1. And we know how big each baseball player is, even if some of that may be actually compiler dependent, but it's however big that thing is. We want another one of those. And so that size of macro works perfect for us. Give me one more baseball player, is what that does. Started with null, so it started with 0. Now we have 1. And now we have to go, we have a string that holds the entire line buff, and we can actually comment out the part where we print the lines for now. We have that string, it's stored in line buff, and we now need to scan the corresponding components from that line buffer. Read from the string the individual components of the file, components of the structure, or the individual data components, individual structure elements, whatever you want to call it here. This part can be a little bit annoying, and we've talked about this before. You have your data structures defined somewhere in your code, and then you have the rest of the code that works with those data structures. You really need to kind of have them side by side. So whether that's two monitors, whether you copy paste that and put it in a comment nearby, you really need to have it nearby, because otherwise you're kind of relying on your memory to make things work. So for me, for now, just so I don't forget what is what, you can always delete this later. It's not hurting anybody by adding extra comments there. That is what we need to read in. Arguably, what could also be useful, again, it's a comment and you can delete the comment later. Let's actually copy in one. What does that look like in practice? These are just comments. These are kind of hints to me as the programmer right now. What do I have in my file? What is now inside that line buffer? How do I actually grab that value that I have here? I have a string. I need to parse stuff out of that string. Things like, well, what do we have? It's defined here. We have to get an integer. Then we have to get a short little string. Then two more strings. Then a whole bunch of integers. Then a few floats. And then a few integers after the fact. What function will allow us to do that? Those of you who had fun with the choose your adventure example should have gotten some experience with this function. It's probably doable without it, but it would be a lot harder without it. scanf, and it's exactly the same as our scanf and fscanf. One scans from a file, and maybe we could have done all this with fscanf. I think the code would have been a lot uglier. Scanf reads in from the user input. Here, we've read in a whole buffer, and now we're just parsing from that individual buffer. So the function is called scanf. Take in, except I'm probably going to get it wrong. Which one is which? Take in first the buffer, I'm pretty sure, that I want to read from, then the formatting string. Heck, let's just read in one thing for now. And then where you want to put the stuff that is corresponding to each entry in the formatting string. And here's the part of the code that I mentioned you kind of have to get exactly right. If you get it wrong, it becomes a little hard to debug, but you have to go kind of carefully and slowly, line by line. I want to ultimately update my players array. I think the code will be a little bit easier, and that is why I statically allocated that separate player there. Grab that first value from the line buff and store it as player.rank. And then finally, once I'm ultimately done, update your array with the scanned in player. And there I can just now copy that whole buffer. That would be players of not num players, but num players minus 1. Because we have one player, we want to update location 0. When we have two players, we want to update location 1 with that value that we've scanned in. There's still more code to go here. But for now, we at least have something we can test. We probably should test, what is num players first, but that's fine. And just some sort of functionality for printing out the player that looks reasonably good. It doesn't really matter what we wind up doing. We could have written a function for that as well. So printf, something like, here's player %d, and that is player I. We can print, all we really have is, whatever that rank, it was sorted by whatever that rank information is. That's the only thing we have right now. And that's players of I.rank. And maybe at the very end, print a new line at the end. Separate our players, or a couple new lines that separate our players. And the reason the rank and the player information is separate, because one starts at 0 and one starts at 1. But otherwise, so far, appears to be parsing our information. We really just then have to go the rest of the way and parse the rest of the information. So we have our integers are easier. Next, we have potentially the position information. That should just be a string. So we started with, let's go to the back here. We have a 1, we have an integer. It's followed by a comma, so you explicitly say the comma in your parsing string here, right? That I have a comma. You're not going to store that as anything, but that is a comma that's separate from the resulting string I'm going to parse, followed by a string. There's a little bit of, if we're not careful here, there's a little bit of ambiguity. Where does the string start? Where does the string end? In our scanf syntax here, I'm specifying that string I'm interested in next starts after the first integer and after a comma. And they tend to end with whatever you tell it is going to come next. In this example, I want a space and I want a comma after that string. So that is when that string should end. I have to then update a pointer. What is the pointer I should update with my string? Its position. How would I write that? And we've talked, that's a good start. We've talked about this. It's giving me some unhappiness, and I don't know if the warning it's going to give me is very good. Format specifies type char star, a string, but the argument has type char star of 3. We want the location of that string. We can either explicitly pass it the location of the first element in that array, or the name of the array is already a pointer to its first element. And that's one of those other big picture outcomes this semester with regards to understanding pointers. This gives me the address of an integer. By specification, the name of our array is a pointer to its first element. So when I'm reading in strings, I don't actually have to provide the ampersand symbol here. Oh, and I guess I should print it out if I want to show that it actually worked. That is called POS, and then that's that. And that would be players of I dot position. Looks promising. I guess I have to have the data open to confirm that it's correct, but it looks reasonably correct. The first data entry is a catcher. We can do a couple more of these, right? Probably, if we're talking about things I want to copy paste into the code, just to make sure I did that correctly, I probably also want to put that line in there as well, so that I remember what each entry is corresponding to. So rank, position, name, of which because there's a space in it, we probably want to split it into first name and last name. You're going to kind of see where this is going, right? This is going to be a pretty large scanf string to grab in all of these individual components here. %s, that's going to go into player.first and player.last, which we can then print. Of course, once we have this stored in this array of structures, we can do whatever we want with them. We could sort them by last name, and there's good old final player Fakington, as well as all the other names here. I can go through the rest of these examples, but at this point, it's really just typing, right? We can do it, it's just more of the same. For each of the entries we have in our CSV file, we read the whole file line by line by line, and what we're gonna wind up crafting is gonna be a pretty awful scanf string, basically, is what we're going to have at the end of the day. A scanf string in which you really can't afford. You could stop at this point because then we just discard the rest of that buffer and overwrite it the next time around. But we can't skip entries, at least the way this is currently written. You would have to read all of those values to get to the next value in the chain. Are there any other interesting ones here? I mean, not really, right? These %d, 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 and eventually you have to remember, oh, those are actually %fs, and so you'd want to grab those values as %fs instead. But otherwise, that's pretty much it, right? That's that entire example here. So parsing, at least in this way of doing parsing, there's other approaches that involve like special pieces of software to generate parsers from a given specification for a file, tend to involve a lot of that. But we simplify, I think, our coding task by thinking about our data structure first, understanding what is in our actual file, and then composing those two things kind of simultaneously or in conjunction with each other. If I know what my data is going to be, I just build a structure around that. And then you really don't avoid the big, ugly scanf, but it's really just one ugly line in your program versus trying to manage all the complexity of having a bunch of different variables of various names. And that goes to now to our Flappy Bird example, which also does a little bit of that. So I showed this briefly on Wednesday. It is just a curses application, but it's a curses application that's attempted doing something somewhat graphical in nature. And I am not an artist, and they say, what's the line? Great artists steal. So of course you start by just stealing existing, assets that are available. And this game has been fully open sourced, so one is able to find the so-called sprite sheet for at least the original Flappy Bird. A sprite sheet is something that you may or may not have experience with. Think about like old school video games, and you have these sort of 2D objects. It is a way of laying out all the different 2D objects in use of the game kind of all at once. The original, like Nintendo, didn't use sprite sheets as such. They kind of dynamically generated the sprites on the fly. But now you can generate them after the fact, and modern games will use something like this, that the artist for the game, if it's going to at least be a two-dimensional game, will kind of lay out what is all the different pieces of art I need in my program. That's for 2D. The concept isn't really that much different for when you have more generalized three-dimensional graphics. Then you have texture maps instead. The mathematics of applying a three-dimensional texture is different than the simple kind of copy-paste we are doing here, but conceptually it's not that different. They tend to get more complicated, so you'd have a single file for this, and then a single file for this, and then a single file for this, but otherwise it's doing basically the same thing. You have this visual layout in some sort of image file that specifies exactly what you need graphically in your application, and they put that together in 2013, and we steal it today in 2023. And we take a look at this. Well, first off, my first thing I recognize is that it's a PNG file. Do I know how to open up and parse and read a PNG file? Maybe. Give me enough time. I read the spec. I could do it. I want to get this done in like an hour. I don't want to spend days and days and days. So when I want to read and work with a PNG file, what should I do? Very similar to what you should want to do with a JSON file, which is what?
Google what to do.
Well, that's a little too vague. Google might give you a good answer. It's a PNG file, it's an image file. We know how to work with those, right? Existing, open source, well-written library. For us, this semester, that was libgd, right? That graphics drawing library had pretty nice built-in function for just read PNG file and access a pixel at location X, Y, and get all your pixels back out. So for me, that's the first step. That doesn't exactly solve the problem, because we know that once we start to use these external libraries, we have to make sure our environment is set up to actually do that properly. So probably what you do is you go back to a prior project in which we did solve that particular problem, and looking back on those examples, both from lab as well as in class, we have to tell our Replit environment, yeah, there's a couple more packages we want to add so we can actually compile things from that library. Similarly, we have to tweak our make file just a little bit. This was based on the tutorial, to make sure we include those libraries when we actually build our application. So recognizing that there is a library that will solve us a lot of our problems as developers is step one. Step two is actually acquiring and remembering and learning how to use that library. Sometimes it's trivial, sometimes it's quite a bit of work. It's a trade-off of inventing it yourself or using someone else's code. For something like reading a PNG file, which is doable but is a decent amount of code, it probably saves us time. Our other constraint is, let's use our curses library, and same kind of issue there potentially. We want to use the curses library. It's not included by default. We make sure we specify that, and we make sure we tweak our make file, accordingly. But otherwise, we have this file, and we know we can call gd PNG file open and get a handle to the entire file. And we know we can decide that I want the particular pixel at the locations corresponding to this friendly little bird right here. We still have to now understand our data. Just like with the CSV file, we have to understand our data. Now with this new capability to write data into files, we can also cut down a lot of the messiness, nastiness of what could be in our code by recognizing that the image file is part of what defines what imagery, what sprites we want to have in our program. We also should create ourselves a separate file that describes what is inside this file and what do we actually need to extract from this file. So for example, this is a particular bird. Let's go to the very first bird that we have here. And I just have it in the image editing application. And I don't really know if there's a better approach to work with images than having it open in an image editing program. And it's zoomed in quite a bit, so that's why you can see the individual pixels. I kind of like this program because it provides a nice, clear interface with regards to what did I just select. And it does say, I selected in the top left, it's very tiny, I don't expect you to be able to read this, location 264 across, 64 down, and the rectangle was of size 17 by 12. I can read that, I don't expect you to be able to read that. That is where that particular bird is located in my program. It is very common in terms of separating out the assets from the core logic of our program, and then separately separating out the core logic from the visualization part of our program to then specify a file that encodes that information separately from the actual image itself. That is my .dat file here. And I did a few because I got lazy, but you could do all the sprites in the program if you'd like to. Specifically, I decided, let's give it a name, string, and then I don't know, this is kind of a hybrid CSV kind of file, but it's basically the same as that MLB Chicago Cubs baseball player file. It's not so different, right? I didn't include a header because I wrote it. I don't need a header because I wrote it. I don't need anyone to tell me what's in that file. It's only for me. But specifically, that's what I encode in that file. Start X, start Y, width, and height. Or I guess name, and then start X, start Y, width, and then height. And if you want to add more images, or more sprites, you just specify where in that file they're located. If you had 10 different image files, you would also probably have to specify which file you're reading from first, but otherwise, you have this kind of metadata associated with the file. You could instead have hard-coded in your program how to draw the Flappy Bird, right? But this way, we've kind of separated out our assets from the main core logic. Next step, we have this file, we have the image file, we have this file, we know we're going to load this file into some way, shape, or form in our program. We would want to do the same thing as we did for the Chicago Cubs example, which is recognize we need to have some sort of data structure to encapsulate that information, to kind of store that information. And this one's actually easier than the Chicago Cubs example. And if you take a look at this code, that's sprites.h here. And ignore my trying to be too clever with like debugging macros, but our main sprite data structure here, I put a valid flag, which probably wasn't necessary, I don't use it, but I define my struct, I call it sprite struct, and it has exactly those values. Start X, start Y, width, and height. And then also, we do know that corresponding to that sprite are going to be the actual pixels associated with the sprite. The actual values that when I go and use like the eyedropper utility, color picker utility, is going to return back out. Usually I can see that here. I might have deleted it. View, somewhere you can see the color information in this application. I may have deleted it. Maybe it's, anyway, you can see the actual color associated with it, color picker. Let's see if I click on that. It used to be in here. Maybe it's up here. There we go. Okay, thank you. It'll give me the actual value in that image. It may not be stored as such, but in that image, as I click on this kind of darkish yellow here, it's got an R value of 207, a G value of 194, and a blue value of 44. We still have to inspect and ensure the pixels are actually stored that way, but at least that's opened in this image editor. Those are the values that I'm getting back out. I need, as part of my data structure, a way to store those values. I don't know how large my sprite is in the general sense. Yeah, that one is 17 by 12. But in the general sense, I have a sprite. I don't know how large it is until I've actually read in that file. Now I'm back to needing dynamic memory allocation. Two-dimensional array of pixels. You could treat it as a single-dimensional pointer, but it probably makes more sense to have this two-dimensional dynamically allocated structure for it. So there's a lot of code here. I won't be able to walk through all of it, but we would have a function that doesn't look too different from what we've done before with libgd, where we specify the name of a file, we open it, and then there's that function we've used before that says, give me one of these image objects based on that file that's open, and it's hopefully able to successfully find that file. And then separately, we'll get to drawing in a second, separately we have to actually load all those individual sprites. And now this code shouldn't look that different from the Chicago Cubs example. It's doing a little bit more, but not that much more. Given my image and given the name of that .dat file, I even call it, I'm very consistent if nothing else, line buff, right? That's the next line of the file that I am reading. I open up my file, fopen in read mode, spit out an error if it's unable to open that file. We're consistent if nothing else, right? While not end F EOF, while we're not at the end of the file, read a line from that file, parse that next entry in the file. In my code, if you see a printf here, it's because I screwed something up and had to debug it. But otherwise, we wouldn't necessarily need to print out at that given point in time. I did that a little bit different than the example, whereas in the MLB example, I was loading directly into the structure itself. That would be a little tricky for a couple of these, but instead, just created a local copy of all those entries that were going into the structure. I don't.
What's percent
Half word unsigned. That's me being too clever. So a 16-bit unsigned integer. I was really concerned about saving 2 bytes there. Otherwise, %d would work perfectly fine. FB sprites, I must have statically allocated because there's no dynamic memory allocation going on here. You think I'd remember the code I wrote 1 day ago. Where is it though? FB sprites, Flappy Bird sprites is here somewhere. That's a good sign you wrote too much code. Might be in main. Nope, it's hidden. Give me a second. Sprites.h, external sprite struct, FB sprites. So I put that in my header file so all my functions are aware of this global variable. It's defined somewhere with a max number of potential sprites here. So I don't dynamically allocate, but I just update the corresponding components in the structure with what I just read in from my scanf like we just have. Now I know I have a width and a height, but I have this pixels array, and we played around a little bit with this code structure earlier in the semester where we should allocate the memory corresponding to however many pixels we actually want. One way to do so is to first allocate a series of basically row pointers. Give me height number of row pointers, and then for each one of my row pointers, allocate an entire row, allocate with number of actual integers. So that's kind of a 2-step dynamic memory allocation. If you look back on lecture 6's slide on this topic, it's exact copy paste from that code that we have there. Give me this many rows, give me this many columns for each of my rows. That's why it's in a for loop here. Then I have to actually go through then and copy the data from my PNG file into that local pixel. And there's probably other ways we could do that. But first we use that get pixel from the file, and we're starting at some start offset in the X and the Y direction. Working with images, and one library uses X and Y, and your code uses I and J. It's really easy to mess that up. And fortunately, it'll very helpfully crash if you do that wrong. And then update the corresponding entry in my pixels, which I then just kind of copy the pointer back over. I don't have to explicitly copy that data back over. So I have my local sprite. I've read in all of my sprites. Except for that 2-dimensional pixel information, it's basically the same exact thing. So we separate our assets from the rest of our game logic. In theory then, any kind of program you want to write that has a sprite sheet, you could then write a .dat file in your own format for it, and really you don't have to change hardly any of this code. 2 or 3 lines of this code is what you really all have to change and should work for your purposes as well. We also generally want to separate out kind of the display from the game logic as well. We are limited if we're going to use end curses to do things the end curses way. That tends to lead to more code that we have to write than we would typically want to. But a lot of what we write here should look very similar to what you would write for all of your curses related code. I just wrap some of it into a curses setup function. Pretty much, unless you have some special needs, you can copy paste that. I mean, it's going to be mostly the same. There's also a cleanup if you want your shell window to look good once your application actually ends. And then for my purposes, and where the majority of the time was unfortunately spent in this program, I had to think a little bit more carefully about colors than you typically would in your bog standard curses application. Most curses support in these windows supports 256 colors, which is enough. That's enough for any kind of NES style video game. And the NES doesn't even support 256 colors, but what they support is dynamic changing of the colors, through the logic in the program. Here we have to set up the colors we're actually interested in. So at some point, and there really isn't any getting around it, I have to go and look at my image and figure out what colors do I actually need. Maybe there's a more clever way to do this where I inspect the image and kind of dynamically generate what colors I need for my program. Right now, that involved a lot of, what was the darker yellow we looked at just a second ago? 207, 194, 44, and you see it there, Flappy Bird color number 3. I just needed to have those encoded in some sense. Those are RGB colors and just a custom little color palette structure here. If you do something like that yourself, one thing you do have to briefly recognize is the curse's colors are actually in the range 0 to 1,000. So multiply by 1,000 over 255 if you want to get those red, green, and blue components to actually look good in your curse's window. But that's effectively what a lot of this extra code is doing, and it actually wound up being kind of complicated. Because the other complexity, and you will see this when you try to do anything graphical in curses, is, well, look at that cursor that we have on the right-hand side. I have drawn what could be thought of as a single solid pixel there. But what's wrong with that pixel, that white box? Why is it very unsatisfying to someone as painfully detail-oriented as I am? It's a rectangle, very awful. So you're gonna have very stretched birds, but I want pixelated birds. What you can do in your curses, but it does add some complexity here, is instead you set the background color independently of the foreground color, and to draw a pixel, you actually draw the Unicode symbol for that is called something like lower half square or something like that. The background color becomes a top pixel, the foreground color becomes a bottom pixel, so you can't write a function that draws a single pixel at a time. Instead, what you wind up writing is a function that draws 2 pixels at a time, a top and a bottom pixel. Let's leave things here for today. If there's interest on Monday, we can finish this example, but otherwise we can move on to new topics a week from Monday when we get back to class, okay? Otherwise, enjoy your break, work hard on your projects, and look forward to seeing you then.